and that I think next time I will probably try to put people into rooms according to their machine, because this year we had, so they are quite similar. All the Zeiss systems are quite similar. So even if you have like an A80 or a 780 or whatever, you will understand better. So I will try to do that next year. We are now going to have a nice workshop with Marie Andersson, who works at Berman Labora, Marie, and she works at Berman Labora, the company that represents Nikon in Sweden. She's in our facility right now, and she's going to give us a live demo with two different cameras. So, Marie, please.
Hello, everyone. Now I'm just going to share my screen here. Just a minute. There we go. See if I can get rid of those also. Okay. So we are going to discuss a little bit, and I'm going to demonstrate how different camera architectures can influence your sample, your application. I know that Sylvia has had a really nice lecture with you regarding how different camera sensors works and what is important for imaging. And the two cameras that I have brought here today is two scientific CMOS cameras. I guess you know about those sensors already. But there are a huge difference between them, because the one to the left, that is called 50M, that is a front illuminated CMOS sensor. And if you're looking at the quantum efficiency of that one, and quantum efficiency, that is basically how many percentage of photons that an imaging device can convert into electrons. In a perfect world, one photon should give one electron, but that never works out. So increasing the quantum efficiency will make your camera sensor much more sensitive for dim signals. So the left one, the 50M, has a quantum efficiency on 82%. And the one to the right has a quantum efficiency on 95%. And already there, you realize that, okay, the kinetics camera with the higher quantum efficiency must be much, much more brighter. But there is another thing also that play into account when you are looking at how dim a sample, how sensitive your sensor is, and that is the pixel size. You see that the left camera, the 50M, has very small pixels, only 3.7 micrometer, and the ones to the right has bigger pixels. And this will also come into account. So what I'm going to do is basically, I have already captured these images. I'm going to open an image of each camera, the kinetics. Oh, where did it go? Sorry. There it is. There it comes. No, it just disappears.
What disappears?
The image that I'm opening. Just a minute. Now I'm opening it and it disappears.
Is it behind? Maybe it goes behind your...
It's very strange because I have tiled them. So I should be here. Okay, I'll do it from here instead. There we do have it. It's that one I need. See if I can open it from here. Yeah. Okay.
Yeah.
So as you see, I have captured exactly the same field of view with these two cameras. And right now, it doesn't seem to be a lot of difference between them. But what I'm going to do is I'm synchronizing these two. So we are going to start to zoom in to both images simultaneously. And we are going to take a look at this cell here in the middle. And I already here, I think you start to see what's happening in the right image, that it's very, very pixelated, and we can't really see these small, fine structures that we can see on the left camera. And this is basically due to that we have much more smaller pixels on the 50M camera than we have on the Kinetics camera. But I'm going to close these images because we are going to look at some other information regarding these two sensors. One was back illuminated and one was front illuminated. And instead, we are going to look at what's going on behind this. We're going to look at the image information here. So I'm just going to open up the image properties here on the 50M camera that has a lower quantum efficiency. And I can sure that you can see when I'm taking up the information here, we can see that the exposure time with the 50M is 100 milliseconds. And I'm using 40% laser power on the left one. But on the camera that has higher quantum efficiency, if you're looking at the exposure time, I hope that you can see my pointer. I don't know how to
we
make
can
it.
See. We can read.
I
Yeah,
don't know how to make them
see your pointer.
make those cool pointers. You see that the exposure time is only 2 milliseconds and the laser power is only 6%. So that is a huge difference, especially if you're starting to work with sensitive samples that you don't want to bleach. So I'm just going to do a live image here with this 50M camera.
I have a question,
Yeah.
Marie. Are you imaging with the spinning disk or in wide field?
This is wide field.
Okay.
I'm doing everything in wide field right now.
Okay.
Yeah. But I think you can appreciate that we will see finer structures, even though that the brightness seems to be the similar. We have had to use so much higher power and longer exposure times on the left image. And now I'm going to go to a live image with the 50M, because you remember that the exposure time on this lower quantum efficiency camera, it was much higher. In the Kinetics, we just had 2 milliseconds and we had 6% laser. So we are going to go live with the same settings. And I'm going to magnify this. And now I'm just going down here and saying 6 milliseconds. And let's go down with the laser to, 2 milliseconds, it should be other way around. 2 milliseconds. And here we go to 6% laser. And now looking at the live image, I think you hardly see anything. So I think I need to push the lookup table quite a lot to even get a decent image to see anything here. So this tells us that the architecture of the camera chip, the pixel size, and if it's front illuminated or back illuminated, that makes sense if you have a very dim sample. But of course, as you could see, larger pixels will also give you a lower resolution. But if I'm going to switch back now to Kinetics camera. If we do have a really, really dim sample, there is some possibilities how we can increase the signal, the brightness of the image, and that is to use binning. So this is now the higher quantum efficiency camera with the 6 milliseconds here, and it's even lower laser power now. But I'm going to try to make it a little bit more dimmer, that we are pretending that this is a really, really poor dim signal. So I will capture this one right here. And you see that I need to push the lookup table quite a lot to get a signal there. Binning, meaning that we are combining pixels. So instead of reading out from one single pixel of a certain size, we are combining 2 by 2, meaning that we will have in a perfect world, we will have a 4 times brighter signal, but the pixel will also be bigger. So let's capture an image also now with 4x binning here. And let's compare them side by side. And I'm synchronizing them so that we can zoom in and do the same on all. And I think you already hear when we are zooming out, this is just the 20x. We are zooming in here. I think you will see what's going on here. We have a much brighter signal in the where we have 4x4 binning, and we have a dimmer signal when we don't have binning. But we can keep the exposure time and the laser very low. And if we're looking here at the ROI statistics, the statistics of the image, we can see that the signal to background in the image captured without binning is 7.80 to 1. And if we are clicking on the right image where we have binned, you see that the signal is brighter because we have binning. We are combining the intensities of 4 pixels, meaning that the signal to noise ratio will be much brighter. But I also think that it's clear for you that, okay, we are losing resolution. We don't really see the structures when we are zooming in. But sometimes that doesn't matter. You're just interested to have as bright signal as possible and do not care about the resolution in your sample. On the other hand, if you want to have highest possible resolution, then binning is not a good idea. You can also think about, I'm going to close these 2 images, that we can work with the dynamic range of the image. And the dynamic range is basically the total contrast resolution of the sensor from dark to white. So it expresses basically the ability to see bright and dim structures in the image. And with this camera, most CMOS cameras has different dynamic ranges from 8 to 16. And we are going to start here with 8. Now we are running in 8-bit speed. And as you can see here, you see down in the left corner, you see that the frame rate right now is around 500 frames a second. But I also think that you can start to see, especially if I'm pushing the lookup table a little bit more, you will see that the image is quite noisy. Oh. I don't know what happened here now. I suddenly got some snapshots. I'm sorry for that. I was supposed to turn on the magnification glass. So here we go. So if you're looking at the image here, you can see that it's very, very noisy. Increasing the dynamic range. Also, if you're looking here at the 8-bit lookup table, you see that we only have gray levels up to 255. That is the gray levels. And you see that the distribution is in the lower scale here. We're going to do the same now and capture an image with 12-bit. And with 12-bit, you will have 4095 different gray levels. So we're using the same exposure time, the same laser power. And if you're looking down to the left corner, you will see that the speed has decreased dramatically because the readout of the sensor is not as fast as it is in 8-bit. And looking at the lookup table, you see that, okay, we do have a little bit more grayscales compared with what we had in 8-bit. And finally, we can also go up to dynamic range 16-bit, and now we will have 65,535 different gray levels. And as you can see, the image is darker. We are still in over 100 frames a second. But the big difference here is that we will not get saturation as easy. I can, just to show you, add the saturation indicator. And I will increase the exposure time a little bit, and we'll just capture an image here. See if I manage to get some saturation. No, I need to increase even further in dynamic range. Okay, that's fine. If I now switching to the 12-bit sensitivity, when we have fewer gray levels in the dynamic range, and I'm using the same exposure time and the same laser power, and I capture that one. I think you already see here that we are in trouble because we have saturation. And saturation is not good, because I'm going to just clean up a little bit here so that you see the images clearly here. There. If I remove the saturation indicator here, I will synchronize them like this. And I will also synchronize the lookup table so that we are not choosing the different levels. And I will do like this. So if you're zooming in, for example, on this cell here on the side, you see that saturation means blooming, that the pixel intensities are leaking over to the neighboring. So you will not see any details there. And looking in the lookup table, when you're looking at a saturated image, you will see in the end here, sure, if you see this little peak, here we have a little peak going here. That is the pixels in the image that is too bright. They are outside your dynamic range. So if you have samples that are both very dim and very bright, then you need to increase the dynamic range of the camera. But of course, as you saw, sometimes speed is what you need, and then you need to have a lower dynamic range so that you can get a faster readout. I will again make an image that is very dim. Pretend that this is a very dim, and you can see that it's quite noisy. So let's capture this one. Because what you can do if you have a low signal and you don't want to increase the laser power or the exposure time because you have a sensitive sample, you can always do averaging. And averaging can be 2 times, 4 times, 8 times, so on, so on. I'm going to capture now an image with the same settings with 8 times spinning. That means that we are capturing the same image 8 times. Noise in the image is random. The signal is on the same pixel all the time. So it will basically smooth out those random appearing pixels in these 8 pictures, 8 images. And I think you see already here, I'm going to synchronize it, that in this we are increasing the signal, but we are reducing the noise. And to get the noise visible, I will also take and push the lookup table so that it's synchronized. And you see that even though we're pushing the lookup table, the background, the noise is not that visible, but you can see it clearly in the non-average image. But there is another way of doing this also, because you can apply denoising on the image. And we do have a really nice, let me see now if I can move this.
Sorry, Marie, it looks like the image on the left is not at the same focus as the other one, or something is wrong.
Okay, we can redo it.
I wonder if it was an old image that was kept or something.
Yeah.
I'm not sure.
Let's see. Let's go to the
right.
So now I'm on 600 microseconds.
Right. Yes,
I have no averaging.
No averaging. Yeah.
Yeah. So if I capture that again, I have such a short exposure time, so
yeah,
I'm
it's very short.
I'm a little bit. Maybe it's something with the camera. You see that somehow it dimmer. I think this can have something with the camera
I think it's
readout.
Because of that. Yeah.
Yeah,
I think
because
it's because
I have
of the laser.
Short,
yeah.
Because I have such a short.
Because you're not using the neutral density filter, that's why.
No, I'm not. So, but there is another way of getting rid of noise, keeping the short exposure times on your dim sample, and that is to use some kind of denoise algorithm. And here in this software, we do have this really nice denoise AI. It's trained on thousands and thousands of images on different detectors, confocal detectors or cameras. And what it does is that it smooths out the background noise and keeps the signal. So let's synchronize this also.
So you need to ignore the fact that the image is brighter at the bottom of that end. It's because we have such a short exposure time that the laser has no time to turn on, basically. So the laser turns on while we're imaging.
And as you can see here, the denoised image, if you're looking at the same cell here, this was 8 times averaging, and here we have now the same quality, the same signal, and a really nice background compared with the undenoised, unaveraged images. So that is something that you can do if you still want to have the speed, so you tolerate a little bit of noise in the image. You can always apply a couple of averaging, or you can use afterwards a denoise algorithm. Right. Sorry, I'm losing my voice here now. Also, speed is of course important in some applications. Let's do a time lapse to see the difference between have a long readout time and a short readout time. So let's start with this speed again. And now I'm going to get a good signal to noise here. So I will increase the exposure time a little bit there. And what I'm going to do here is just run with no delay for 5 seconds. You know that we have a frame rate here on 660 frames. So just run and see how long time it takes and how many images we will get in this time frame.
I remind all the point confocal people that we're imaging as 2,400 by 2,400 pixels. 600 images per second.
That's great. And now I'm going to go to the 16-bit dynamic range. And let's first of all just make sure that we have a nice signal there also, like that. And I will go run now. I think you already here in the time lapse can see that it's a little bit slower. And get rid of that one and that one and push the lookup table a little bit. There we go. Synchronize. So in the first movie that we captured with the speed mode where we have a really fast readout, and you can also see that we have a lot of noise in the image. We captured 640 images in 5 seconds. In the one where we captured with a slower readout that is looking very, very nice with black background and high signal to noise ratio, you see that we have 334 frames on 5 seconds. So if you need to capture dynamic event, you might need to sacrifice a little bit of the signal to noise to get the fast readout that you want. So I'm going to open up a couple of images here that I have already opened, and it's that one. And we're switching to Duppy. And let's synchronize them. These three images are captured with different field of view on the cameras. So I'm zooming out, and you can see that this is smallest. It's an 18 millimeter diagonal on the camera sensor that we have captured. There are some cameras that has this smaller field of view. For example, if you have a C-mount camera. This is with 22 millimeter. Some camera sensors, you can capture 22 millimeters. And the kinetics here, we have captured now with 25 millimeter field of view. And I think you can appreciate the size of the images, that we are capturing more cells in the 25 millimeter than in the 18 millimeter. But why does that make sense? Why do you need that? Well, if you are going to do some analysis, for example, let's say that you would like to do a cell count. I have prepared a simple cell count here for Duppy. So let's first of all run it on the 18 millimeter field of view. And let's see how many cells we will get there. 95. This image contains 95 cells. If we do the same now with the 22 millimeter, we have 125 events or cells. That's better. And try with 25 millimeter field of view and see how many cells we have there. 142 cells. So let's say that you are having an application, an experiment where you are looking for some rare events, or you would like always to capture at least 1,000 cells as fast as possible. Then a larger field of view is giving you more counts per frame. So you will faster reach your desired event number, or I can't, they are not focusing at all now.
Sorry?
I'm trying to zoom out, and
To zoom out, yeah, okay.
Yeah, but it's always when you are kind of connected
Right.
to some
No.
kind of
Zoom or something.
Teams or Zoom, it's always a little bit delay. So the size matters in this case, because if you want to capture, for example, 1,000 cells to get your correct statistical values, then it's better to maybe capture a few frames to capture more cells than going with a small frame. And I'm going to live show you this. For example, if you would like to do a live image, it can make sense to have a larger sensor. Now I need to move this and just open up my job. I'm going to adjust the camera ROI here. So let's go for 2048. 2048, you can see that we have a smaller field of view, and I will just run the large image from here. I just need to redefine a few positions here because I have removed the sample ones. So let's set a corner there, and let's go diagonal and take another corner a little bit more. It's not that flat, this sample that I have borrowed from
No,
JJ.
this is what I'm seeing, that the sample is very slanted.
So now we are in the 18 millimeter field of view, and it says here, estimated image size, 16 fields. So we need to capture 16 images to capture my defined stage area here. So let's do that. So it will be a 4x4, as you can see here also. Perfect.
We would need the hardware autofocus to keep all this in focus.
Yeah, but I think the message will be there without the focus. It's not a competition in beautiful looking images. So, and let's go out now to a larger field of view. And if we're looking at that, you can see, oops, it's the lookup table. I am in DAPI. We need to go to, oh, I was in DAPI, the previous one. I forgot that. I thought that I was doing. Okay. So let's do the same large image, starting from here and there. And you see 9 fields. So this will be faster. We will capture the same area, but with fewer tiling. That will be faster. And maybe also save your precious sample a little bit from bleaching. And there we go. And another thing, let's say that, okay, but you don't need this large field of view, maybe, but you would like to capture a larger field with higher resolution, meaning that you can get the same field of view with a 40x objective as the 20x objective. If you're using the larger field of view, for example, 25 millimeter, then you can see the same number of cells with 40x as you can do in 20x in a smaller field of view. So large field of view is quite nice to use when speed is important. The last thing that I think we need to cover also is resolution. And I know that now I don't have the image there because I have switched to kinetics camera, but I have the formula here. And I know that Sylvia has also had this on your lectures. Oh, that was big. And that is, what pixel size do we need to get the best resolution when working with the camera? You know, when you're working with a point scanning confocal, you have control over the pinhole size. You can decide yourself. You can adjust it according to the wavelength, magnification, and numerical aperture. You're deciding yourself. So it doesn't matter. But cameras has fixed pixel size. Remember, the 50M camera had pixel size of 3.7 micrometer, and the Kinetics has a pixel size of 6.5 micrometer. So here you need to make some calculations. So example, if you have a 60x objective with 1.4 in numerical aperture and using 525 as your wavelength, you will use a camera with approximately 6 micrometer pixel size. Would that work for a 20x objective? Well, let us check out. I have prepared some images here with both cameras. It's that one. Kinetics. This is the same cell with kinetics. I'm going to open up cell with the 20x objective also. And they are there. And the final one is the 50M camera with 20x. Kinetics. I'm going to switch place on these two. So in the left row, we have the DS50 camera with the smaller pixels with 60x on the top and 20x on the bottom. On the right side, we do the 50M with 60x on the top and 20x on the bottom. But first of all, let's take a look now on the 60x. The image is captured with 60x. And zoom into the cell to see if we can see any difference. Because the 20, here we go. The DS50 has smaller pixel and the Kinetics has pixel size that are better matched to. And now we're talking about the optical resolution, not the digital resolution. So this to the left should be a little bit more oversampled because you need to cover 2.3 times the pixel size with your
So as I said
it's
in the
2.3 times, right?
Yeah. In the
Yeah.
lecture, what I said is that in the course we calculate with 2x. As the
Okay.
Nyquist sampling, it was just for simplification, but actually for a camera, normally we should use 2.3. So this one, Marie uses 2.3. This is the Nyquist sampling factor that we spoke about.
Yes. So, but what I think is very interesting is if you're looking at the kinetics now with the bigger pixel size, and let's start to zoom into a cell. The below here is the 20x with the smaller pixel size camera. No, the larger, but we have a 20x that should go for smaller pixels. And you can see here when we're zooming in approximately the same, you see that this will not give you the desired resolution at all.
So basically, with the 60x, we are we imaging at Nyquist sampling with
we
the 60x?
are practically almost imaging at Nyquist. The pixel size calculated is around 6 micrometer
instead
and
of
the pixel size here. And the pixel size of the DS50 is 3.76. So for calculating according to this formula, we should have 3.4 micrometer pixels to match.
With the 20x. So basically at the top right, we're imaging almost at Nyquist sampling. With the top left, we're oversampling.
Yes.
And this is with the 60x objective. And
this
when
we
change objective and we go to a lower magnification would require smaller pixel on the camera.
Yeah.
So we are now undersampling at the bottom right, and we are sampling Nyquist on the bottom left.
It's basically because I
Almost.
think the 3.4 micrometer according to Nyquist sampling with 20x objective and the camera pixel size for this camera is 3.76. So, and I think you can appreciate that the cell looks much better for 20x.
Do you have a possibility to zoom in to the same cell, just so that we can compare?
Unfortunately, so the 60x cells, they are the same.
Yeah.
But the other one
not.
I couldn't get back to
I see, to the same
exactly
place. Yes,
to the
yes, yes.
same place. So the 20x cells are, that
Okay,
was my
the same.
plan, but something went wrong.
Yeah,
So,
I wanted to see if we could find any artifacts, but of course, you have to compare with the same cell, so it's okay.
so unfortunately, I didn't manage to do that.
Okay.
Only for 60x and for 20x
Yeah.
comparing to each other, it worked out. But I think it's quite clear looking at using wrong camera uh, with the objective you desire, and using the wrong pixel size of the camera will not give you a good result if we're looking at the
So if you
20x.
remember, this is why sometimes we add some magnification
Yes, I was
when.
just about good that you reminded me. Because we can, on this microscope, there is an extra additional magnifier lens that we can add that is on the microscope that gives you 1.5 times extra magnification. And if we use that with the same wavelengths, the 525 and 20x objective here, then we should have 5.7. If you calculate it according to Nyquist, the pixel size should be 5.7. So we are closer to Nyquist by adding the 1.5. I can actually, if we have time, do that.
Yes,
I,
yes, you have. Yeah.
I just wanted to say that when you zoomed out before, you were at the same place for the both 20x's.
Uh-huh.
It's not possible. Okay, we can check that later, but maybe that cell was there somewhere, but it was not in the. So I will add this 1.5 extra magnification now. Yes, it's
So you're
there.
using the 20x, yeah?
We are in the 20x now, and
20x objectives, yeah.
kinetics, and I'm going to go to 555 excitation. So now we are, so let's just choose a cell here, and can take this one, for example. Focus on those, capture the image without the 1.5 extra magnification. Oh, you see, where did the image go? Did I not capture it? That was very strange. So this is now, the live image is without the magnification lens. Capture that one. There it goes. I think I still have the problem with
The
short
laser. It's
the laser.
Too short exposure time.
Yeah, exactly. So what I'm going to do is actually I'm going to,
You can put in the new
yeah,
ND filter,
I can do that. And
and
maybe
then you
go
have to
to,
push the lasers and stuff.
yeah, there we go. And just going for saturation, no. Something like that.
Mm.
So, okay, focus, capture.
So that was without or with?
Yes, that was without, and it was completely black. So let me see.
You have too low laser.
Yeah.
Oh. You can add the other neutral density filter in the excitation wheel.
Yeah, I think I'll do that.
Yes. No.
That's better. So I'm going to close this one, mess things up here. So now I'm capturing without. There we go. And I'm going to just remove it, or add it, I mean.
The lens, the extra magnification lens.
Now I'm adding the extra magnification lens, and we will capture that one. There we go. And take away that. Wrong shortcut. So to the left with the extra magnification, and to the right, the one without. Zoom out. It became very low resolution.
Yeah, I think you were a bit out of focus there.
I think I don't get it why I had like the custom 680, 680. That was not optimal. This was new for me. Oh, it's calculating it automatically when you're adding the lens, or what?
Can you change the sensitivity, the bit depth, just to see if it resets
Yes,
it?
I'm going to.
We still have very, very few pixels.
That was very strange.
Yeah. Okay.
Actually, this I don't really
Okay,
get.
that I've never seen either.
No, I have never seen that.
Looks
So
like we have discovered the bug.
yeah, I think we have discovered the bug. So let me see if I can.
No, it doesn't move. Just change camera and go back, maybe.
Yeah, maybe I can just.
Yeah.
It tells me that you see that I actually do not have that much pixels in my,
No, exactly. So
in my
it's cropped
camera.
somehow.
They
Yes,
look good.
I think you need to move,
Yeah, I'm gonna do
change to
that.
the camera and then,
I'm gonna do one of these.
or the with the other camera. I know.
Yeah, I changed with the other camera now.
Right. Yeah, that's our world is a lot of a lot of troubleshooting all the time.
Hmm.
Now I think we will need to restart the camera. Something went wrong there.
Yeah.
But basically, this was the idea with the extra magnification lens. If we have a to be Nyquist, the magnification on a camera-based system, the magnification matters for the digital resolution. I think you might want to restart NIS.
Yeah, I was just thinking maybe I can do it with the 50M camera, so I'm just going to go for the
Right.
555 instead. See if that is listening to my wishes regarding the voice.
So in some of your systems, I think you have also this extra magnification lens. With some manufacturers, it comes by default with the microscope, and for others, it's an option. So you have to basically buy it.
Shutters. There. Oop. Okay. Now I will capture. Let's see if we can get. Now I capture this without extra magnification, right? And I will add it. And capture. So to the left, it's without extra magnification, and to the right, we do have the one with extra magnification. Maybe the focus position was not exactly the same.
Yeah.
I can actually try to capture the one without again. See if they can get one better. So now we are 1x zoom. that was terrible.
Need to refocus. Just zoom in so that you can see better. Ah, yeah, you don't have the wheel thing.
I can do this. When I'm not having that, I can use this.
Right. That looks good.
Okay. So many pixels. This is the full resolution of the camera now. So now I will capture that one. And just let me clean up a little bit. That one also. Now we do have the extra magnification lens to the right, to the left, and the one without to the right. Oh. So I think you definitely can see that it's difference in resolution in the left one where we're using the 1.5. But now we are with smaller pixels also. So this was not really we switched camera to the smaller pixel size. So whoa.
So basically, when we go down, when we use an objective with a lower magnification, like the 20x, and we would require a camera with smaller pixels, and so we can add magnification. So we go back and forth with going down in the magnification with the objective, but increasing the magnification afterwards. But basically, this is the way we can basically make use, like go to Nyquist sampling with a lower magnification objective. That's the only way we can do. So on the back camera-based system, we're a lot less flexible than on a single point confocal, but we have some little tricks like binning and adding the extra magnification lens where we can change the pixel size of the image. And you can see at the bottom, if you can show Marie, where the pixel size is in the image.
Here it's in blue, 0.07 micrometer per pixel in the one where we have used the extra magnification lens, and 0.11 for the one where we are so
good,
increasing the pixel size basically. And that is the same as we're doing when we are using binning. With the addition that binning also give you an increase in signal that should be approximately the same amount of binning. You should see an increase in signal. That is, if you do 2 times binning, then it should be a 2 times increase in signal intensity also. All right, I think we are out of time, right?
Yeah. Are you said what you wanted to say?
I think that was the last thing